A 1,200-pound chandelier is to be suspended over a large ballroom. The chandelier will be hung on two cables of equal length whose ends will be attached to the ceiling, 16 feet apart. The chandelier will be free hanging so that the ends of the cable will make equal angles with the ceiling. If the top of the chandelier is to be 16 feet from the ceiling, what is the minimum tension each cable must be able to endure? We begin with a diagram so that we can make sense of the situation. We have a rectangle representing the ceiling of the ballroom. Vectors F1 and F2 represent the two cables of equal length that will be suspending the chandelier. The chandelier is being represented by an oval, which we're told in the problem weighs 1,200 pounds. Vector F3 represents the 1,200-pound force from the chandelier. We can see that the ends of the cables are 16 feet apart and that the chandelier is hanging freely 16 feet from the ceiling. We have two angles labeled alpha in the triangle. Our first task is to find the angle measure alpha. Because vectors F1 and F2 are equal in length, we have a triangle that's an isosceles triangle. Thus, the dashed segment labeled 16 would be an altitude of that isosceles triangle. Therefore, it divides the length between the cables, 16, in half equally. Thus, the distance from each cable attached to the ceiling to the dashed segment labeled 16, each of those distances are equal to 8. Now we can find the measure of angle alpha. We know that the tangent of alpha would equal opposite side 16 over adjacent side 8. 16 over 8 reduces to 2, so the tangent of alpha equals 2. Using a scientific calculator, we will find alpha by taking the inverse tangent or the arctangent of 2. Rounding to 3 decimal places, we find that alpha is approximately equal to 63.435 degrees. The three angles of our triangle must add up to give 180 degrees. Two of those angles are alpha, which we found to be 63.435 degrees. Thus, the angle between the two vectors F1 and F2 would equal 180 degrees minus 2 times 63.435 degrees. This is equal to 53.13 degrees. Thus, the angle between the two vectors F1 and F2 is equal to 53.13 degrees. Using alternate interior angles, we can find the angle from the horizontal to vector F2. That angle would have the same measure as angle alpha, which is 63.435 degrees. To find the angle from the horizontal to vector F1, we need to add 63.435 degrees plus the angle between the two vectors, which we found to be 53.13 degrees. That sum is 116.565 degrees. We will now write vector F1 as the magnitude of vector F1 times the quantity cosine 116.565 degrees times I plus the sine of 116.565 degrees times J. This is equal to the magnitude of force vector F1 times negative 0.44721 I plus 0.89443 J. We will write force vector F2 as the magnitude of vector F2 times the quantity cosine 63.435 degrees times I plus the sine of 63.435 degrees times J, which can be written as the magnitude of force vector F2 times the quantity 0.44721 I plus 0.89443 J. Force vector F3 can be written as negative 1200 J. Since the system is in equilibrium, we need force vector F1 plus force vector F2 plus force vector F3 to equal 0I plus 0J. This means that the magnitude of force vector F1 times negative 0.44721 plus the magnitude of force vector F2 times 0.44721 plus 0 must equal 0. And also, the magnitude of force vector F1 times 0.89443 plus the magnitude of force vector F2 times 0.89443 minus 1200 must also equal 0. Our first equation will yield the result that the magnitude of force vector F1 equals the magnitude of force vector F2. We now give this magnitude a common name, say magnitude of force vector F, and we will substitute that into equation 2 for the magnitude of F1 and also the magnitude of F2. Making those substitutions and adding 1200 to both sides of the equation, we now have 2 times the magnitude of force F times 0.89443 equals 1200. Solving for the magnitude of force F, we have that the magnitude of force F will equal 1200 divided by 2 times 0.89443, which is approximately equal to 670.82. Therefore, the cable must be able to endure a tension of approximately 670.82 pounds.